30.1% of the numbers on this planet start with the digit 1. The digit 1. This is known in mathematics as Benford's law. Hi, I'm Jesse. This wall behind me is real. I will show it to you. But what I want to talk about is that 30.1% of the numbers on this planet start with the digit 1. And to be precise, it's 30.10299995%, which is the log of 2. So we press 2 and then the log. 2 log. So this is how many numbers start with a 1. For example, if you look at the number of inhabitants of cities, let's say, for example, Amsterdam, let's say 800,000, 850,000 or something, I don't know, but then it starts with an 8. But that happens not really often, that a number starts with an 8, and I can calculate that. It's log of 9 minus log of 8. It's only 5%. 5% of the numbers you will find in your newspaper start with an 8. So you should, or you could think, when you think about it, that it doesn't really matter with what number a number starts, like that there are the same amount of numbers that start with a 9 as with a 1, or with a 2, 3, 4, 5, 6, 7, 8, 9, that it's just totally random, but that's not the case. This is known in mathematics as Benford's law. And it was actually not found by Benford himself. It was found by Simon Newcomb in the 19th century. So how did he find that? In that time you didn't have calculators. So when you had to multiply numbers, you had to take some kind of table, logarithmic forms, and look it up, like take this number and then take times this number is another number. And when he took that logarithmic table books, he found out that the pages of the numbers that started with a 1 were more dirty than the pages that start with numbers that started with a 9. So he was like, why do people use pages of numbers that start with a 1 more often than pages that start with a 2 or 3 or 5, and the pages with the numbers that started with 9 were almost clean. So he thought, why do people use it more, these pages? And then he really found out that there are more numbers starting with the digit 1. And he also found the logarithmic relationship for the first digits of numbers, and that is a logarithmic relationship. So he could really calculate the numbers that start, the frequency of numbers that start with 1. So he didn't get the credits for this discovery. It was Benford. So maybe I could explain what my thoughts are on this. Or let's say first, of course, not every set of numbers obeys this law. For example, the height of people almost always start with 1. If you measure it in meters or centimeters, like 183, like my length, and there are not many people that are less than 1 meter. Okay, maybe children, and there are not a lot of people larger than 2 meters, so there maybe 60% starts with a 1. But if you look at all kind of numbers randomly taken from all kind of sources, then it converges to this Benford's law, and that has been proven mathematically by a professor from Georgia Tech. But an example of numbers from one source is, for example, the length of rivers. So, and this can be understood because the length of rivers it can differ a lot. Like you have rivers of only a few kilometers and up to rivers that are more than 1,000 kilometers. So there you have a few different length scales. So ranging a lot of scales. And what I mean with scales is like in between 1 and 10, in between 10 and 100, in between 100 and 1,000, and 1,000 to 10,000. So immediately when some set of numbers covers a lot of scales, then you converge to Benford's law. So more digits more numbers start with a 1 and less with a 9. Okay, it also depends that we try to write down all numbers with only 10 digits. But this also happens when you use another base, for example base 20. Then less numbers will start with the number 19. For example, the Mayas calculated with base 20, but then it does not really depend on the base 10 that we use, like the 10 from the 10 fingers. So it happens with all bases larger than 1, even if you use a non-integer numbers as a base. That's something I studied myself. Okay, one thing about Benford's law is that if you measure all numbers in, for example, meters and kilograms instead of miles and pounds, for example, it doesn't matter if you rescale all numbers from kilometers to miles, for example. Actually, this frequency distribution is the only distribution that satisfies this scale independency, scale invariance. So, for example, with the rivers, if you now calculate everything in miles, it will have the same closeness to Benford's law. So then the numbers are exactly close to the 30% as in miles or in kilometers. It doesn't matter. I don't say it's exactly this number for the length of rivers, but it's close in miles or in kilometers. So that's the scale independency of Benford's law, which is also understandable, because if there is some tendency towards some distribution, it should be scale independent. So the uniform distribution, where all digits have the same frequency, from 1 to 9 as the first digit, cannot be a tendency, because if you then recalculate everything in another measure system, it will not tend to the same distribution. So Benford's law is the only distribution that's scale independent for the first digits. So if there is some tendency towards some distribution, it can only be Benford's law. It doesn't say that it should converge to some distribution. One thing that you can do is, how I think about it, is that we use numbers from 1 to 10, we only use one digit. Then from 10 to 100, we use one digit in front of the other numbers. Then from 100 to 1000, we put another number in front of it. But all these intervals are different in size. Now, if you take the logarithm of these numbers, they have the same size. 10 to the power 1, 10 to the power 2, 10 to the power 3. Then all these intervals have the same length. So that's something about the logarithm.